Hi, my name is Li-Feng Cheng. It is my pleasure and honor to speak in this forum. I will share with you my view on beyond 5G towards 6G. 5G commercial system has been launched since April of 2019. So far, most of the mobile network operators system offer 5G eMBB services, which is coexisted with 4G system. We call it non-standalone system that utilize 4G core net functionalities. Beyond 5G system at minimum, I think will be multiplexing of eMBB, URLC services with end-to-end slice to support application within the same service class across different service classes. This slide shows the outline of my talk, infrastructure for B5G, overview of Taiwan MOEA-funded 5G program, and moving toward pre-study on 6G and opportunities. So this slide shows an IoT platform architecture that can host 5G promise service, including eMBB, URLC, and Massive MTC, which is a complete integration of 5G plus IoT plus AI and sensor networks. Multi-range support, it is essential either for 4G, 5G, or 4.5G coexistence, or 5G Wi-Fi, or any other combinations. Domain-specific interfaces here are needed to support applications deployed in different vertical domains, such as industrial IoT, teledrone, for public safety, or disaster recovery, smart city, telemedicine, etc. In each vertical, mixed applications, each corresponds to different service classes or flow, will then need to be carefully managed based on the required QoE. Network resources availability and other measures. So each flow or each service, we will need a virtual path from application to the end devices. It has to be established. So what will be the infrastructure, the core network that will host this entire, will host this service, or a platform that has a combinations of three services, eMBB, URLC, and Massive MTC. So for the 5G infrastructures, for B5G, beyond 5G infrastructure, whether it is for private enterprise network or mobile network operators, public cellular network, the key technology pillars are cloud-native 5G infrastructure that include service-based 5G core network, Open RAN, specifically O-RAN design that allows inclusion of AI or machine learning in radio resource management, planning, and other features. Disaggregated distributed edge computing is also needed to reduce the overall network latencies to support the URLC services and to reduce the loading in the core network. And AI or machine learning assisted network management and operations will be needed to optimize the network performance. And lastly, the infrastructure should be flexible enough to support end-to-end network slicing. How do we make it flexible? I think cloud-native 5G infrastructure is a key component there. So first, I will say a little bit about service-based 5GC or service-based architecture here. Here is a high-level diagram for service-based architecture and interfaces, where control plane consists of network function module. We also call it service modules here, with a simple request reply, subscribe notification messages that will use HTTP2 application layer protocol to convey these messages. So the service-based 5G architecture will be used to design the 5G core network. 3GPP 5GC is actually based on this a framework. This is a logical architecture of key 5G network functions. This is not meant to be complete since there are other functions such as network exposure function, network registration function, and AF function are not shown here. As you can see here, this is a control plane, and UPF is a data plane. This design allows for control data path separation, and it also allows scaling depending on traffic loading, as well as we can independently restart or remove or replace a module. For example, these modules are all stateless modules. It can be replaced, restarted, or I say isolated if a failure or if one of the modules is under attack. So this is a quite flexible modules. And this one is another key system is an key subsystem is Open RAN, and this one here I shows ORAN based architecture. And this architecture has a couple of features here, which is the entire RAN. It used to be a standalone one unit, integrated unit. Now it has a disaggregate RAN. It's separated into a DU, which handle IOC MAC file design, and ORU include RF and some of the physical layer low-fi digital processing, such as FFT, EFFTs, and the CU centralized unit, which has a control plane and a user plane. And this will be all in a cloud infrastructure. And this infrastructure there will have white box, allow the white box hardware servers can be used to host CU, DU, and other RIC functions, radio intelligent control functions here. The hardware box will have general purpose processors, GPPs, and accelerators. Each of those modules can be should be containerized. So the network functions will be containerized in to fit into this cloud-based architecture, cloud-native architectures. An important features here is the here there's orchestration and automations. This will allow the service management and orchestration. This is a service management and orchestration framework. It will manage the RAN nodes, each node here, the transport, the hardware, and the cloud infrastructure in a unified manner here. So the cloud infrastructure monitoring, the life cycle management, and the things will be managed in here. And some of the other, like a manager for your radio resource management, radio infrastructure management, the management of ORU, the management of the DUCU, the resource and memory usage, and monitoring the resource and memory usage will be done all in these modules here. Okay, and most importantly, there's a non-near real-time and near real-time modules is a RAN intelligent controller, RIC, near real-time IRC, and non-real-time. The non-real-time, the criteria here is for non-real-time which is greater than 1 second RAN intelligent controllers. And then near real-time is, of course, is below 1 second. These are mainly, the purpose here is this, you see the A1 interface. The purpose here is to enable AI ML to support radio resource management applications. And AI ML intelligence is expected to enhance the effectiveness of the previous for some of the features in 4G zone, like CCO and PCI allocations, and advanced RM radio resource management use cases. In particular, I think based on the white paper, those related to traffic steering, QoS, QoE optimization, RAN slicing, and massive MIMO will be able to use AI to assist it to perform all these functions. So we cover the O-RAN-based architectures and the infrastructures, the co-enabled infrastructures. Next, I will go over the Taiwan MOEA supported 5G program. Taiwan has a very strong ICT industry, and disaggregation of 5G infrastructure, as I shown in the previous slides, and the open RAN framework open up the new business opportunities for many manufacturers. The Beyond 5G program is a government-funded R&D project in its second phase. The project is performed by the two research institutes, E3 and III. The first phase 5G program started in 2017 and ended 2020, which is overlap is the second phase program started in 2020. The first phase program has done development of the small cells for both sub-6 and millimeter wave. So it's a standalone small cell solution. And we leverage those design to expand it to include, to work on the second phase that include the open RAN, support the open RAN infrastructures. So the first ways, we also have done the end-to-end infrastructure solution for enterprise network and the POC trials. So the function like for IGC, 5G core network MEC, OAM, operation and management function, we have done some of it in the first phase and has been completely containerized using native, cloud-native Kubernetes platform, and it's all containerized. We also have done some application and have those applications done in field trial. That's in phase 1. So several Taiwan's ICT companies have transferred the first phase result from E3 and III and have done license transfer. So this slide just briefly shows the second phase, and we are working on the CU-DU-RU here. The RIC function, as shown in the previous slide, based on O-RAN infrastructures, we are working on the softwares for the enhanced OAM function and the more 5G core network functions such as network exposure function and network registration function, as well as some of the element management function for each from MEC, 5GC, and passes to OAM. So the OAM is done for both infrastructure and devices. We also are working on the end-to-end private network turnkey solution that can provide service. We're looking to the best solution here, integrated this into our overall end-to-end solution. The application on the application side, the second phase, will have 3 applications, a few trials. It's drone racing, smart manufacturing, mainly focus on digital twin with some of the AI capabilities and with the UILC base station to support these services. And smart hospital, which include location tracking, telemedicine, and AR-assisted medical services. And for the drone racing, it includes technologies for digital front-person view for live broadcasting of the event, handover using real-time IC, close real-time IC with AI to predict its handover path. This is the general program. In addition, we also have collaboration ongoing project for EU-Taiwan collaboration, which we believe will pave a path towards 6G application, in particular for remote assistance via digital twin. In 5G, the on-site operator will be technician, whereas in 6G, it will be robots or robotic arm. The two projects started in September and November 2019, respectively, which one is 5G Dive, the other one is 5G County. This one started in September and November of 2019. This is a 2 years program. This is 3 years program. So this one will be ended end of this year. The two pilot projects, two pilot verticals in 5G Dive are Factory of Future, including digital twin and autonomous drone scouting for emergency rescue services. Drone carries camera flying over the disaster area to detect persons in need for help, so that the rescue team can dispatch helpers to the needed area in time. So in Taiwan, the partner are ESCI, NCTU, National Chiao-Tung University, E3, and III, as well as Far East Tong. 5G Coney, Taiwan participant Alpha, Chunghwa Telecom, E3, and III. The 5G Coney, this is a 3-year project, as I said before. It built 2 field trials, one in Bosch and another one in Taiwan's Taichung in intelligent manufacturing, located in Taichung. 3 use cases will be trialed in here. Use case 1 and 2 are related to data collection and AI modeling, and AI modeling based on the data collected to provide predictive maintenance and the remote assistance via AR or via MR. Okay. Use case 3 is for connected robot and will be done in Bosch factory. So this is a summary of a B5G program. Moving towards 6G. Moving forward, we have done a pre-study on 6G and its opportunity. We have organized an expert group to conduct a pre-study and a review of the worldwide 6G academic activities. Committee members for this group are mostly from academia. The purpose is to explore potential applications and identify technologies that are essential to support these applications. The group looked into 4 specialty areas, namely applications, communication, material, and semiconductor processing. From the review of the worldwide 6G activities, the committee summarized 9 anticipated applications, requirements, and the technologies to support these applications. So I will summarize this in the following 2 slides. In short, 6G has the following features. Ultra coverage. 6G access technology will not limit to cellular. it will integrate with a non-terrestrial network, LEO, and high-altitude platform stations. And thus, it will provide coverage from sea to ground to air that is 10 kilometers above the ground. And it will have AI-assisted wireless communication networks for network operation optimization and management, deployment automation to reduce CapEx, performance optimization via prediction and self-recovery and auto-scaling. Interaction between cyber world and physical world via immersive technologies. So this slide shows the 9 applications. Several applications involved in immersive technology used in different environments. E-health, industrial IoT, via tele-robots, where user in the physical world is connected with the cyber world with a sense of immersions. So there are 9 applications. I will just briefly describe it. This unmanned vehicle, this is a multi-purpose unmanned autonomous vehicle for land, sea, and in the sky communication. And a surgical training simulation via digital twin of human body and tactile internet. Remote operation, this is interactive remote robotics. Remote operation and control of the on-site robot-assisted application in manufacturing. This is familiar holographic 3D telepresence. And of course, public safety here is also a very key area, the ultra precision location tracking for public safety or disaster recovery. Ubiquitous network provides coverage from sea, land to air, as I mentioned. It's just not a cellular network. It's also connected the high altitude base station or the non-terrestrial network. And AI intelligence IoT things. This network provides a multi-dimensional massive intelligent IoT devices. Every device has the capability to intelligently detect its surrounding and decide what to do next. AI everywhere. And ultra precision location tracking criteria is 1 meter outdoor and 10 centimeter indoor. So these are brief description of the applications or the enhanced user experience 3.6E. This slide summarizes the attributes for 6G. I think within next 5 years, RF components in here we don't dare to look into a terahertz frequency band. I think it's ultra frequency band. In Taiwan, we probably will focus on 100 to 300 or even below 200 gigahertz area for the RF component or RF subsystem, and in semiconductor processing for the RF components, the processing technology for RF components there. So this is overall, I think the group summarizes in the 6G attributes based on some white papers and among the from the sources listed here. So these are the what we think the group survey result review. I see the attributes of 6G and the applications that these attributes, the application that have the following attributes. So how do we get there? We may start with low power consumption, the opportunities. We have to be realistic. This slide shows ICT ecosystem in Taiwan, from modules, this industry, from module to the core infrastructures. We have industry that can do develop modem, chipset, and have a fab that can do gas, Ghana Estron, and the GAN processing technology, and the PCB board. And devices, for example, module, AR, VR, glasses, smart glasses, and smartphones. And small cells, and we have quite a few small cell companies, and server storage. In the infrastructure side, switch routers and high performance computing servers, and most importantly, for the for cooling technology, the immersion cooling system here. So, what do we see the opportunities here for our industry here? We see start with for more close to 6G, we see like we can start with low power consumption, high frequency RF components design, for example, the high speed ADC DAC, and PA for power amplifier for wide bandwidth 200 wide bandwidth power amplifier, and high frequency power amplifier. New material and advanced processing technologies for RF front end. For beyond 5G, several areas for infrastructure side, we can build in 5G ready software into routers switches to optimize network performance. A true O-RAN solutions, a multi-RAN capable private network solution, including light 5G core, software-defined NFV open networking with some software enables there, and intelligent network management, as well as cybersecurity. We can embed some of the software solution into our hardware platform so that make it to be a 5G ready. So I think all these present a great opportunity, a potential opportunity to the ICT industry. So this is what we have in mind for beyond 5G towards 6G. So for 6G, I think initially we will start with some of the high power, high bandwidth, high frequency RF design, and associated processing technologies. This concludes my talk, and thank you for your attention.